Hello everyone, I am Dr. Rukmini from Department of Astronomy, Osmania University, and I am going to present today a talk on my research work, photometric study of 61 totally eclipsing contact binaries from ASAS, OGLE, HATNet, AST3 and TESS database. A typical night sky would look like this, jeweled with hundreds and thousands of stars of different colors and brightness. And if one is lucky enough to have clear dark skies, the sight of Milky Way patch, our home galaxy, would be a real treat for our eyes. But how do the stars actually form? Their birth is a tug of war between two dominant forces acting on the cold molecular cloud, the seeds of star formation. Here you can see in this simulation a contracting gas cloud, molecular cloud, and wherein the bright patch, yellow patch, is the hottest and densest region where it is condensing due to gravity and the thermal energy is pushing the matter outwards. These forces, gravity, collapsing matter inwards, and thermal pressure acting outwards, would come in an equilibrium and then hold the stellar structure of stars. More than 70% of the stars in the sky are either binaries or multiple star systems attributed to the origin. Following are this number of simulations created by Matthew Bate and for formation of binaries and multiple star systems. You can see here that there are various factors like mass of the cold molecular cloud, the turbulence, influence of environment, the magnetic field, metallicity, chemical composition, density, temperature, size of the molecular cloud. All this would be inherently responsible for the formation of either binaries or triple systems or multiple systems or a single star. And it also controls the rate at which the stars are formed and number density of the stars which are formed. So what are these binary systems? Can we see them? How do they look? What good if we study them? Binary star systems is a pair of stars bound by mutual gravity and orbit around the common center of mass. The hotter, brighter component is called primary, and the fainter component, less massive component, is called as a secondary star. They appear as single star even through the telescope, but the periodic brightening and dimming of the starlight, which is also called as light curve, coming from the system due to their mutual eclipses, help us in understanding the nature of these two stars and of the orbit, etc. Here you can see that the two stars are orbiting around the common center of mass, and this plot, which is plotted with respect to time and brightness, the brightness variation is recorded here, is shown. And you can as well see that as the inclination of the plane of this orbit changes with the sky, with respect to the line of sight, the shape of the light curve also changes. So there are various other factors which may influence the light curve. So let us find out if some of them which we can see. One of the popular constellations in the sky is the Big Dipper, the Big Bear, also known as Saptarishi Mandala. The stars famously called as Alcor and Mizar or Arundhati Vashishta are seen here in the naked eye observations as double stars. But through a telescope, one can see that the Mizar, the brighter one itself, is resolved into two components, and there is a relative motion between these two components found in the observations. Of course, a better telescope actually reveals that none of them are single stars. Even the two components of the Mizar themselves are binaries, and as well the Alcor is a binary system. One of the popular constellations in the winter skies is Orion. which is also called as the hunter. And adjacent to it we find a bright star called as Sirius or Alpha Canis Majoris, a dominant star in Canis Major constellation. Though visually it appears as a single star, single bright star, it is resolved as an astrometric binary by telescope. So you see here, this is an optical image of Sirius, wherein the bright star is Sirius A and the faint star is called as Sirius B. One specialty of this system is that faint star in this system, which is in the visual observation, is actually much brighter in X-ray image. This is the image taken by Chandra X-ray telescope, wherein you can see compared to Sirius A, Sirius B looks much brighter. And this is not because of, as you can understand, because this is being observed with an X-ray telescope, it means that brighter in the X-ray emissions, it's a very compact object. So it is a special object known as white dwarf, a very hot compact remnant of a dead star when matter is in the state of electron degeneracy. So what do we do to study them? We do take observations. The first one being visual observations, or called as imaging, where the periodic changes in the relative positions of the stars, of both the stars in the system, help in studying them. For example, as we have seen earlier, Mizar A and B, or else there is another example known as Centauri, Alpha Centauri, and the two components' positions also relatively change with time. Here you can see another example, Capella, wherein the two components were imaged 1 week of time separation. You can see that the relative position of the components change with time. So in the imaging method, the relative positions of the components are recorded, and then the orbital elements derived for the system, and successively followed by deriving the physical elements. Other methods which are followed and only a brighter star of binary is visible, not the fainter one, the fainter one is not resolved even with a telescope, are shown here. One is called as astrometric, photometric, eclipsing binary system, and spectroscopic binary star. So depending on the method which is followed in observing them, these binaries are categorized with these names. Some binaries which have very low inclination with respect to our line of sight or in the sky plane, we can see that the brighter star would be observed as wobble in the sky. So the wobble of the brighter star, like in this case for Sirius A, will reveal the binary nature of the system. Some other systems with high enough inclinations of orbital planes are studied by spectroscopic methods, but definitely they need to be brighter systems. So here a Doppler shift observed in their spectra, the spectral lines that show periodic shift, red shift, and periodically being shifted towards the blue end. These kind of observations reveal the binary nature of the system. Now what is happening here? When the fainter component or the brighter component is moving in the line of sight towards our observation, towards Earth, in the direction of Earth, or away from the direction of the Earth, you find that their spectral lines are either blue or red shifted. This is one of the best methods to estimate the mass of the stars, mass of the components, using Kepler's laws. So other than Sun, apart from Sun, spectroscopic method is one of the best method in estimation of masses of the stellar objects. So, and Here you can see the another method which is also called as photometric system, photometric method, wherein eclipsing binary stars are studied. So in the photometric method, the mutual eclipses of the two stars, two components, would periodically increase or decrease the brightness of the system. Depending upon the brightness of the star which is being eclipsed, the dip has a different depth in the light curve. So what you see in this window is known as light curve, wherein brightness of the system is plotted with respect to time, and the depth of the dip depends upon the amount of light which is being blocked during the eclipse. So here is the theoretical observation, and this is called as a light curve, simulated light curve. Here you see the brightness variation plotted with respect to time or phase, which are periodic. But you can see the difference in the shapes. Here you can see that the highest brightness region is flat here, it is curved here, and here the minimum brightness region is almost the same for both the eclipses. Okay. So the region of the light curve where the brightness becomes maximum is known as maxima. The region where the brightness of the light curve becomes minimum in the graph is known as minima. So these are phases, maxima phase and minima phase. Similarly here, this is the phase of maximum brightness, this is the phase of minimum brightness, and similarly in the third light curve too. So the difference in the shapes actually are related to the system itself. What you can see here, some of them are cartoons, but some of them are actual observations. So depending on the shape of the light curve and the prototype system which was discovered first with these light curves, they have been named as EA eclipsing algol types, EB beta Lyrae types, EW W-UMA types. Here the classifications, as I said, are named on the prototype. So algol types means they are having light curves which are similar to that of another binary which is called as algol, similar to W-UMA and beta Lyrae. So once again, a light curve is a graph plotted for the variation in the brightness of the system with respect to time. And when the brightness is maximum, that region is known as, that part of the light curve is known as maxima. When the brightness dips to certain minimum value, that is known as minima. You can see here, when the brighter star is eclipsed, you have a maximum dip. When the fainter star is eclipsed, you have a smaller dip. So when you have a longer dip in the brightness, it is known as primary minima. When you have a shorter dip in the brightness, it is known as secondary minima. So a typical light curve will have maximas separated by primary minima and secondary minimas periodically. And in this cartoon, you can see how the shape of the light curve can be related to the physical parameters, to its orbital parameters of each of the components and the system. Such kind of observations, continuous observations, help us derive various characteristics of both the stars, which are listed here. So you can see we can measure, as I said, from Kepler's law, we can measure masses once you know the period of the binary system. Whenever one of the components or both the components orbit around the common center of mass, making one cycle, the time duration is known as the period of the binary. So using Kepler's law, From the period, one can derive the mass of the systems. And you can as well see, depending on the sizes of the stars and depending on the temperatures, the bluer, more the bluer being eclipsed, more would be the depth of the dip, and redder star being eclipsed, depth would be less. The bigger star being eclipsed, depth would be varying, right? So we find that on depending on the sizes of the secondary star which is orbiting around the primary, you can as well see the slope of this millimass in the light curve. So many other parameters like surface activity, metallicity, magnetic fields can be derived from the light curves, and subsequently these may also help in deriving the distances, metallicity, evolutionary stages, or even the existence of exoplanets from the light curve studies. The current work is on the data taken from some of the ground-based observing missions, and one on space-based observing missions. We have analyzed over 61 totally eclipsing binaries, which are also called as WUMA binaries, EW type binaries, from these missions. Let me define what is called as a contact binary. As you can see in one of these cartoons, you can see that the two stars are orbiting about the common center of mass, just like the above ones. But there's a difference. You can find that their atmospheres are actually in contact. In such kind of stars, we find that there is a mass transfer taking place from one component to another component of the binary. Let me briefly talk about these various missions. The first one is ASAS, and it stands for All Sky Automated Survey, and it was observed in 2004. Around 2004, more than 11,000 stars were observed, and more than 2,000 eclipsing binary stars were observed, of which 1,317 contact binaries were existing. So we had chosen 2 objects from this catalog. There is another catalog, OGLE, Optical Gravitational Lensing Experiment. Basically, this experiment was designed to find if there are any exoplanets, and the light variations are the major measuring techniques which are used to detect exoplanets. So in the process, they have discovered many eclipsing binaries, more than 4 lakh eclipsing binaries, and we have chosen 48 of them as totally eclipsing contact binaries for our analysis. The third one is the HATNet, Hungarian Automated Telescope Network Survey, and in this survey, most of the galactic plane which overlaps with the Kepler mission has been observed, and the accuracy is very high. Here we have chosen 3 objects from this mission. There is one more mission at Antarctica where an array of Chinese telescopes, small Chinese telescopes, are held under Dome A, and we have taken 6 objects from these observations. And the latest one is the TESS, Transiting Exoplanet Survey Satellite, which is a space satellite, a space observatory, and its mission has recently been extended till 2022. It was commissioned in 2018, and very good observations were released in 2019, and early even till 2020 they are getting the observations. So from the initial data which was released in 2019, we have taken 2 objects which were showing totality and a contact binary nature. Now, as I said earlier, partially eclipsing contact binaries provide very poor estimate of masses. Here let me define one term called as mass ratio Q. So we say that the contact binaries which have totality would provide reliable values of mass ratios Q if you are observing them spectroscopically, else even the photometric observations provide you equally reliable mass ratios if they are found to be totally eclipsing. Um, so let me give you a summary of the objects which have been collected in all these missions. We have the list of missions stated here and the number of objects. I wanted to highlight this one thing. We see that some of the missions are have observed objects in the direction of disk of our galaxy, whereas OGLE has observed the objects in the direction of bulge. So it has observed in other parts of the galaxy also, but we have selected our objects from these regions. And contact binaries have typical property of short periods. Their periods lie very, very close to 0.2 days to 1 day. So 1 day in the sense 24 hours, 0.2 days is 20% of 24 hours. It's very small, few hours, less than half of the day. So the two sun-like stars would orbit around the common center of mass, just zipping about within 8 to 12 hours around the common center. And of course, this table also provides you with the effective temperature of the system, stellar system, which would actually reflect the effective surface temperature of the primary star. We have used this tool known as PHOEBE. PHOEBE is a complex tool which is based on GUI, graphic user interface, and it is used to analyze both the spectroscopic data and photometric data. And when you provide suitable input parameters and run the program, input parameters in the sense from visual observations of the light curve and all other data, the brightness, magnitude data at various filters, and the shape of the light curve, the spectral type of the system, which you can infer from the various magnitudes or from previous spectroscopic data. Of course, even before giving an input of all other parameters, period is one of the important parameters. So we derived the periods for all these 61 binaries using another application called as PHOEBE. And the light curve analysis was done using Wilson-Debeny code, and which is an authoritative code in photometric study in the whole of the eclipsing binary research area. And this is an older version of PHOEBE. The new version has additional advantages, and it runs on Python code. So the important parameters like mass ratio Q, effective temperature T, the normalized light of the whole system L, the angle of inclination of the plane of the orbit with respect to the sky plane, the gravitational potential of both the systems omega. So these are taken as input parameters, and iterations are performed using the Wilson-Debeny code till a synthetic light curve is generated, providing minimum error between the synthetic and observed light curve. So sigma O minus C square between the observations and the synthetic light curve typically has to be as minimum as possible, which means the theoretical light curve or the synthetic light curve which has been derived should be matching very closely to the observed light curve, and hence the parameters which are estimated during this analysis would be representing the true parameters of the given. This analysis was performed individually on all the 61 totally eclipsing contact binaries, and after the best fit, the results obtained are shown here. The selected binaries fell in the range of very short periods, low mass ratios, F2K spectral types, with some having lower degree of contacts called as marginal contact or contact systems, and some showing higher degree of contact called as over contact or deep contact binaries. See, our intentions were to determine these kind of parameters for contact binaries, for eclipsing binaries at various places in our galaxies, various positions in our galaxies. We wanted to know if there are some parameters where the system would be where the system would reflect being in a crowded field like in the bulge of the galaxy, and where the system would be reflecting that it is in a scarce field like that's in a newly forming star forming regions like in the disk of the galaxy or in the halo. So our intentions were to study all kinds of systems which behave in a different way at different places of a galaxy. This is one example fit of the light curve plotted from the analysis. This is for an object taken from OGLE mission. Here once again, as you can see, on y-axis you study the variation in the brightness. Here it is written as magnitude. You can observe that the magnitude scale is in the reverse order compared to that of brightness scale. So this is a typical method, a parameter called as magnitude, which runs in a reverse order compared to brightness of stars. And on x-axis we define the orbit, periodic orbit of the stars in terms of phases. So one orbit would be covering one phase, 0 to 1. So when the phase is 0.5, you find one eclipse, and when the phase is either 0 or 1, you find another eclipse taking place in the system. Here the red dots represent the observations taken from OGLE, and the black curve represents the theoretical light curve which has been derived using the photometric analysis from PHOEBE. We clearly see that the fit is very good. The brightness is continuously varying as defined for a contact binary, and we have flat minimas which is typically observed for totally eclipsing binaries. Here are rest of the 60 light curve fits. So you can see that the selection criteria was mostly having selecting those binary stars which were showing flat minimas, eclipses, flat eclipses, and giving appreciable amplitude of the light curve and showing least scatter. This is a large scatter here, but still minimum compared to amplitude of the variation in the light curve. These are another set of light curves. Now let us see some of the characteristics of these binaries and try to understand the feature of the systems. This is a plot of period versus mass ratio, and the various stars here, small stars, represent a catalog of objects which were studied by PHOEBE et al. And Sisbedia, Davidson, set of objects which were cataloged by them. And on the backdrop of this, we have overlapped with them the plot with our objects. The circles represent our objects here. Here we represent the third axis, fillout factor. Fillout factor will actually tell you what is the extent at which the two stars are in contact. So more the fillout factor, higher is the contact between the two components. Closer are the two cores of the stars with respect to each other. So we have another plot here, similar to the previous one, with the third axis representing the temperature, showing the objects with lower mass ratios having higher effective temperatures, and for the of the primary or for the system, brighter component of the system. Other plot, which is known as period versus effective temperature. Sometimes the temperatures are derived using the magnitude difference in the two different filters of photometric observations. So they are also called as colors. So this plot is mostly plotted with respect to period and color. Now we have plotted it with respect to period and effective temperature. Again, we have used the extensive database which was already existing. So there is a curve which is defined here, the thick black line, which is also called as SPBE line, short period blue envelope theoretical line. So most of the sample stars from the database actually fall onto the SPBE line, and which represent average sample of contact binaries with the shorter periods in their young evolutionary stages. So any overcontact binary above this line has to evolve towards longer periods and cooler temperatures, theoretically. Binary containing these objects would be losing angular momentum, spinning rapidly, decrease in its period, and its fillout factor increases, the contact degree increases, and the cores come closer to each other and undergo mergers. They become single stars. For contact binaries, such mergers result into a typical kind of stars called as blue stragglers. Here there's a plot of derived mass and radius, which is actually related for contact binaries dependent on their mass ratios and periods. Here the theoretical plot, the green, red and blue line represent theoretical plots for single stars, individual stars. So we see that all these circles represent primary component, the brighter component, more massive component of the binary, and the stars represent less massive component of the binaries. So what we see here is the primaries follow a linear trend, whereas the secondaries show a scatter. Of course, even when the primaries follow a linear trend, the slope is different compared to that of all other single stars, and the primary stars are within a region of these two theoretical lines. Now, the green line, theoretical line, represents stars known as ZAMs, zero-age main sequence stars, and the red line represents stars known as terminal age main sequence stars. So all the stars which are existing between these two boundaries, they are actually young stars. Main sequence stars are called as young stars. So we see that the primary stars are existing exactly within the main sequence phase. However, the secondary components have evolved beyond the main sequence. Now let us come back to the conclusions. We see here that all the objects in study are short period late type binaries. Late in the sense the spectral types are from F5 to M0. All the binaries are totally eclipsing with mass ratios being reliably determined. The absolute parameters have been derived using gaseous relations, which is dependent on mass ratio and periods. Of course, the mass ratios which have been derived are very low, with massive primaries and less massive secondaries. However, few systems are having very low mass ratios, which are interesting for further follow-up observations, as these very low mass ratio with high fillout factor and short periods are suspected to be target objects for mergers. And out of 61 objects, 15 are found to be marginal contact binaries, showing lesser degree of contact. But however, 31 objects were found to be over contact and 15 with deep contact configurations. The fillout factors were more than 50%. And these were in the direction of bulge region. The higher temperature differences between the components for some of the systems could be due to transition between the contact and broken contact phases of the system, which is also called as thermal relaxation oscillation model, which is also observed as with low fillout factors being evidences. Characteristic plots imply that most of the binaries in the sample are evolved systems, with the secondaries being over luminous compared to the primary ones. The results add on to the existing evidence that in short period contact binaries, late type systems are more in frequency compared to early type contact systems, based on the evolutionary history of contact binaries. The correlation studies and the calibrating empirical relations across the entire range of parameters will act as a strong tool for further calculations of physical parameters of contact binary stars. And such studies, more in number, in the short period cutoff range, will allow correlations to be tested actually further and improved upon the results in the evolutionary models. The current paper I have presented last year in international conference on universe of binaries and binaries in the universe at TELC, Czech Republic, and the details are available in the conference proceedings as cited here. This is our team. We have been working on various kinds of binaries using both photometric as well as spectroscopic methods. And of course, a part of our research also is extended to study of existence of exoplanets using photometric study of binaries. These are the references and of course resources also, which I have used in making this presentation.